Hello, we are Beacon, Biometric Electromagnetic Airway Confirmation for Optical Navigation. A 3-year-old presents to the emergency room unable to breathe. Physicians quickly attempted intubation, but the child's small anatomy made correct placement of the tube within the trachea extremely difficult, leading to multiple failed attempts, critical delays that ultimately result in the rapid oxygen desaturation of the patient. As a direct result of this desaturation, this patient suffered from hypoxia and other cardiac complications. This results in further medical stay that for prolonged treatment that costs an extra $8,500 per day. This desaturation, unfortunately, is all too common in emergency rooms across the United States, with nearly 1 out of every 6 pediatric patients experiencing some kind of extreme desaturation event during the intubation process. This is so dangerous because patients who have saturation drop below 80% have an overall 80% increased risk of mortality. With this in mind, pediatric intubation is clearly a very critical yet difficult process to perform correctly. There are several tools that help to facilitate this process, but they have key limitations. For instance, the video laryngoscope helps the clinician to visualize the airway in real time, but doesn't actually provide correct, accurate confirmation of placement of the tube within the trachea. CO2 capnographs, conversely, are able to validate accurately that it is placed within the trachea, but only once the procedure is finished. Therefore, we created Beacon to address these need specifications, to be able to provide clinicians with accurate feedback that is placed in the trachea, provide real-time guidance while guiding the tube, and be optimized for pediatric settings and emergencies.
So Beacon addresses 3 main clinical gaps aligned with the current intubation procedure. First is accuracy. We want our device to ensure greater than 90% specificity and 90% sensitivity, and this is a standard for CO2 capnograph. We also want to provide real-time guidance where we have less than 100 millisecond latency with greater than 200 hertz sampling. This will provide real-time guidance to the physician as they're performing this procedure. And finally, we want pediatric optimization where our device can provide clinical support for physicians who's performing this operation. So Beacon seamlessly integrates in the current intubation workflow in 4 simple steps. First, the patient's neck circumference is measured. Then a Beacon sensor is then placed on the patient's chest. Then a Beacon magnetic stylet is then used to intubate the patient. And then finally, the Beacon box performs computations and provides a feedback on the physician as they perform intubation procedures.
So Beacon's hardware revolves around 3 key components: the Beacon box, which houses all internal electronics, as well as the display for setup and real-time guidance, our custom-made magnetic stylet, which is used to actually guide the intubation procedure, as well as provide the magnetic field that's read by our sensors, and of course, our 2 sets of Hall sensor patches. Then, in order to calibrate Beacon, all Beacon devices undergo the following calibration procedure at manufacturing to allow them to interpret the raw voltage values from the Hall sensors as physical distances. And this calibration remains stable over time, so there's no need to recalibrate Beacon before emergency usages. And then finally, in order to calibrate Beacon on a patient-to-patient basis, we found this NIH pediatric CT scan database and annotated 300 scans, in which at sensor locations 1 and 2, we measured the esophagus and trachea depths from the chest, as well as taking the neck circumference about sensor 1. We then fed this data set into a machine learning model that will allow us to directly correlate the neck circumference with locations of the tubes for our sensors. And this means that practitioners simply need to measure the patient's neck circumference, set the patches, and they're ready to intubate with Beacon.
So the way Beacon is able to determine which tube the stylet is actually in is first the clinician takes the measurement of the patient's circumference, pass that through the ML model, the pre-trained ML model, and then from that we are able to get the estimated trachea and esophagus position for that patient. Simultaneously, we get Hall sensor readings and we pass that through an inverse physics simulation and then pass that through a Bayesian state estimation algorithm. With that, we are able to continuously localize the stylet, and because we carefully derive and quantify uncertainty throughout, we are able to make a statistically grounded, calibrated inference. This is what the clinician will see. As you can see, the classification, the confidence of that classification, and the position are all ready to see.
So, to recap our progress, the proof of concept used modular Velcro Hall sensor patches to detect a basic linear voltage through an Arduino. Our proof of concept was also capable of basic airway classification. The next iteration of Beacon, the minimal viable product, used additional patches all stored within one singular electronic storage box. We also then created a machine learning algorithm for classification and depth detection. This version of Beacon, the MVP, also included our first fundamental UI for basic visual interface of tube location and depth based off a pediatric model system. The final iteration of Beacon integrates 5 major upgrades from the MVP. First, we've integrated over 300 CT scans for precise airway modeling. We've then also added an HDMI touchscreen for emergency usage and optimized our algorithm for dynamic positioning. We transitioned to fully medical-grade 3D printed sensor patches, which has all been tied together under one singular intuitive UI. For hardware specifics, our 200 Hz HDMI screen runs off of a Raspberry Pi and Arduino Maker 1010 for little to no latency. The magnetic slide has been metal printed and validated on a pediatric mannequin as well.
So we have also added a dynamic tracking layer to Beacon. It starts with an estimate of the stylus position within the patient. As well, we have the uncertainty propagated through the model in that estimate. We pass that through a kinematic motion model to predict where the stylet would go next. Then we pass that prediction into a magnetic forward model to predict what the Hall sensors are going to read. And then we get the actual Hall sensor readings, combine them, and then pass them through a Bayesian updating filter, which combines them and refines the prediction. This happens 200 times per second to make it such that as time goes on, the prediction gets better. This is the launch screen for the Beacon UI. As you can see, it is very quick and intuitive to quickly put in the neck circumference as is required in the ER. And once tracking begins, this is what the clinician will see. The classification and confidence of that classification is clearly viewable from across the ER. And using the new dynamic tracking, we are able to visualize the position and uncertainty of those positions to better inform the clinician.
And here, so you can see an image of our actual fully integrated our hardware and software with the stylet, our patches, and the enclosure holding the HDMI touchscreen for our GUI. We wanted to move on to testing this fully integrated system. And first, we started with baseline testing, looking at accuracy, specificity, and sensitivity. And so to do this, we did 3 replicates of 25 esophageal and 25 tracheal intubations. And then we looked at whether we got a true positive, true negative, false positive, or false negative. And that was displayed on this confusion matrix. And from this confusion matrix, we were able to calculate our accuracy, sensitivity, and specificity, all of which came out to 96%, passing our need specification of 90% that we defined earlier. And further, we looked at the actual model confidence output that's displayed in the GUI during these cases of true positives where we intubated in the trachea and it read trachea, or false negative where we intubated in the trachea but it read esophagus. And we found that the model was very confident in these true positives, which was a great thing, and not very confident in the false negatives. So even when the model was predicting incorrectly, it wasn't showing high confidence. We also wanted to test in more like human-like conditions. So we took the mannequin and we used saline solution and to simulate some sort of sweat. And then we did the same test that I just described. And we found that there was no real significant difference between the dry and wet testing conditions. Finally, we wanted to kind of look at user error in placing the patches, because this is obviously something that could happen. And so we did this by either rotating one or both of the patches or displacing one or both of the patches horizontally from the midline by 1 centimeter or 30 degrees in terms of rotation. And we made this heat map. So we did 10 trials of each of these conditions. And we found that on these initial tests, displacement of the patches had a far greater effect in causing Beacon to perform worse in accuracy compared to something like rotation of the patch. Although we would like to test more intermediary conditions and more extreme rotations and displacements. And then we also wanted to look at time until confirmation and compare that to a standard threshold of 60 seconds for use when using something like a video laryngoscope and CO2 capnograph. And we made this histogram after one of our team members did all these tests. So this is from setup to actual confirmation from the GUI. And we had a mean confirmation time of 34.5 seconds, which was performing favorably to the standard threshold of 60 seconds. Now moving on to challenges and next steps. Of course, we anticipate challenges with clinical translation as we haven't tested with actual physicians yet. So we want to get into the hands of doctors, nurses, other healthcare providers who are actually going to use the Beacon device and see what they think about how we can integrate into clinical pipelines. We also anticipate some issues, or have had some issues with model accuracy in kind of edge cases where they're like pediatric patients, but they're either very small or very large. And so we think that we can stratify the model across the subgroups of pediatric patients to improve the accuracy. We also have some issues like in challenging raising of the signal to noise ratio. And so for like when the depth gets very low, the signal to noise ratio becomes an issue. So we want to have a stronger magnet in the stylet to improve upon this. And then we also have anticipate some issues with signal interference in noisy settings where there's some magnetic interference, such as a hospital. And so we would like to actually test our device in hospitals, and then from there use that data, maybe integrate some filtering hardware to improve that signal robustness. Overall, Beacon is a fast, reliable intubation confirmation support system for pediatric emergency intubation, and we are very happy to continue working on it in the future. This is the team. We would like to thank our mentors, and we are happy to take any questions.
So one of the questions I had was, especially in kids, the intubation, the tube might be of a different size and have other different physical characteristics. Have you guys looked at different physical sizes of the tubes, since pediatrics is, from little babies all the way up?
Yeah, so we've tried with multiple tubes. We have various diameters. We know the average diameter of a pediatric patient can vary from like 4 millimeters to 20 millimeters. So it's pretty modular. Probably the biggest limiting factor would be the size of the magnet we need to use. So we have tested it and need to do further testing to be able to fully validate it. But we believe that just by being able to change the diameter of the magnet and therefore the outer circumference of the stylet, we will be able to optimize to smaller anatomies.
Got it. Thanks. And then my second question was, have you given any consideration to the different types of airway obstructions that these kids might have when you're trying to use this technology? And I guess, I don't know if this is a related question, but how long does it take to measure the neck circumference? Have you looked at how physicians could make errors there?
So that's a great question. With regard to the different types of obstructions, we haven't fully validated all of that yet, but we believe that things like clots or bloody airways, this will help to overcome some of those challenges, because we're once again not relying on a video laryngoscope. We're using the sensing tracking to be able, so it will become independent of what we actually visualize in the airway. But that is a great suggestion that we'd like to incorporate going forward, various obstruction tests. And then, sorry, could you remind me of the second question?
Sure. The second one had to do with the ease and ability to measure the neck circumference, which seems like it's important for you
Yeah.
guys to do.
So we don't have data exactly on, we haven't done measuring the neck specifically, but that is lumped into our data of the 34.5 second trial in the histogram that we showed a few slides ago. Basically, we started from, patient lying down, measure the neck, put the tube down, and wait for confirmation. So that was incorporated there. I'm sure there's some other noisy and obstructive happenings in the ER that might make it a little prolonged, but our initial tests indicate that it wouldn't significantly or detrimentally impact the amount of time it takes to intubate.
I guess just to quickly add on to that, it was a team member doing the tests, right? So we're kind of used to measuring the neck circumference, so we really need clinicians to test it to really kind of make a conclusion on that.
Thank you, Team Beacon.